welcome to a lesson on polar graphs. In this video we will take a look at some of the common graphs of polar functions, including roses, lemniscates, and lemacons, and we'll look at what their equations look like and how those are related to the graph. So let's start with the lemniscates. Lemniscate equation has the form r squared equals a squared sine of 2 theta. Or if we could do the same thing with cosine, r squared equals a squared cosine of 2 theta. So the basic questions we're going to ask in all three of these examples, all three of these functions. One, what's the basic shape of the graph? Okay, so if I tell you you have a parabola, you know what that looks like. So if we have a lemniscate, what does that look like? Okay, then we'll look at how does the graph change depending on whether it's a sine or cosine graph. We'll then look at the constant that's in the function, which in this case there's only one constant that's going to change, and that's the a. But we'll in some of the other ones we'll have different functions. And then we'll want to look at where does it intersect the x and the y axes. So to get started to look at these functions, lemniscate, let's look at this polar graphs. It's a GeoGebra applet. So if you haven't yet, go ahead and pull that up. Okay, so on this graph, we have a polar grid, and there are 3 boxes in the corners. We'll go through each of these one at a time. We have roses, limacons, and the lemniscate. So let's start with the lemniscate. So again, remember, we want to figure out what is the basic shape of the graph, how does it change if it's sine or cosine, what does the constant or constants do to the graph, and then where does it hit the x and the y axes. So let's start first. So again, we see down here the equation is r squared equals, and right now it's 1 squared sine of 2 theta. And if we look over underneath the checkbox, there's a slider that controls the value of a. Okay, so right now a is 1, so that's why it's a 1 squared sine of 2 theta. And I have it set to sine. Okay, so as we look at the graph, it kind of looks like this is maybe a figure 8 or sort of like an infinity symbol, something like that. And it looks like it's sort of centered. Maybe we'll make it a little bigger here, but it looks like it's centered along the diagonal line, the y equals x, or the 45-degree line. So let's see, let's first play around and see what happens if we change the value of a. So as a gets bigger, what happens to the graph? Right? Well, it looks like the graph gets bigger. So right now a is 6. So what do we notice about the graph? Well, the graph, again, it looks like it's a figure 8, or sort of an infinity symbol, and it looks like the radius, we'll call these 2 petals. So the radius of each of these petals, of each of these loops, extends out to the 6th circle. So they have a radius of 6. And if we look at our equation, it's now r squared equals 6 squared sine of 2 theta. Sometimes you may see that as 36 sine of 2 theta, but again, we'll realize that the radius is going to be 6. So it looks like the general shape so far is just going to be this this double loop kind of graph, and we know that if a gets bigger, so we know that a represents the radius of each of the loops. So let's see what happens if we change it to cosine. All right, so it's still the same shape. It's just kind of angled at a different direction. So again, if it was sine, it runs along the diagonal 45-degree line, and if it's cosine, it's going to run kind of symmetric about the x-axis. Okay, so for the lemniscate, the 2 main things we want is a is the radius of the petals, and then we need to know if it's cosine, it's on the x-axis. If it's sine, it's on the y equals x line. If it's sine, where does it hit the x and y axis? Only at the origin. What about if it's cosine? Well, it hits at the origin still, but also at plus or minus 6 on the x-axis. Okay, so that's the lemniscate. It's pretty quick. So let's take a look at our next function. All right, now let's go ahead and take a look at the rows. So the rows of the equation, it's a little different. No, it's not r squared anymore. It's just r. So we have r equals a. We still have an a again. R equals a sine, but it's not 2 theta. Now n theta. Or similarly, r equals a cosine of n theta. So we're going to go through the same series of questions. What does the basic shape of the graph look like? How does it change whether it's sine or cosine? What do the a and the n do to the graph? And then just kind of get sort of an idea of where does it hit the x and the y axes. So let's go back to our graph. All right, so back on our graph here, let's deselect the lemniscate and let's go to the rows. Okay, so in the rows, again, we now have two sliders. We have one for the a value and one for the n value. And then we have the ability to change between sine and cosine. And then down here we see our equation, r equals 1 sine of 1 theta. So let's first just play with a. So if you look, remember what it did with the lemniscate, the a told you how big the graph was. So in this case, a is 1. Well, it looks like similar. This is a petal, so the loop of 1, radius 1. It's actually a circle of radius of a half centered at 0 and 1/2. But so as we make this bigger again, so we have a circle. So if you ever see a graph of r equals a sine of theta, you're actually going to get the graph of a circle. It's centered here at 4, and then the radius is also 4. Okay, so if it's just a 1 in front of theta, it's a circle. What happens if we change that to cosine? Well, cosine, same basic graph, but now it flips over to the x-axis. Okay, so if n is 1 and 8 is our a value, this is a circle of diameter 8, which means its radius is 4 and it's centered at 4, 0. All right, so let's go back to the sine graph, and let's take a look at what happens if n changes. So right now n is 1 and we have one circle. What happens if n goes to 2? Well, so now that n is 2, we suddenly have 4 loops, or since it's a rose, and this is why we call it rows, it has 4 petals. Okay, so we went from 1 petal, 1 loop, to 4. So what happens if n goes to 3? Well, now at 3, we have 3 petals, or 3 loops. If n goes to 4, so if we have r equals 6 sine of 4 theta, we now have 1, 2, 3, 4, 5, 6, 7, 8 petals. If we go to 5, we have 5 petals. If we do 6, we have 3, 6, 9, 12 petals. So we can keep going. So hopefully we can see a pattern here. If n is odd, so 1 is 1 petal, 3 is 3 petals, 5 is 5 petals, 7 is 7 petals. So it would stand to reason that if we had n was 9, we'd have 9 petals. So if n is odd, we have that number represents how many petals there are. So what if it's even? So if n is 2, we have 4. If it's 4, we have 8. If it's 6, we have 12. If it's 8, we have 16 petals. So if n is even, so again we have 6 sine of 8 theta. If n is even, we actually have 2 times that number, or double that amount of petals. So if n is 8, so say this was 6 sine of 10 theta, we could expect that there would be 20 petals. We double that number. Okay. So looking at, so we got a lot here to look at here still with the roses. There's a lot going on. With an even number of petals, where does the graph hit the x and y axes? Well, right now with 8, it's only hitting it at the origin. With 6, it's only hitting it at the origin. I mean, it kind of loops out, but it's not touching any of the axes, just at the origin. With 4, it's only hitting it again at the origin. All the petals are inside the quadrants. So if n is even and you're dealing with a sine graph, you will only touch the axes at the origin. So what if it's odd? So if n is odd, we touch the y-axis at 6 and the origin. If n is odd again, now 3, we touch it at, we have 3 petals, and we're going to touch it down here on the negative y-axis and at the origin. So we're touching it here at the 6 because that's what our radius is. If n is 5, well, 5 goes back up the y-axis and the origin. So where do you think it's going to go if we did 7? It's going to go back down. Okay, so there's a bit of a pattern here. 1 goes up, 3 goes down the y-axis, 5 goes up, 7 goes down. So if I had n was 9, I can't do it here, but if n was 9, we could expect that the one pedal that's on the y-axis will go up the positive y-axis. Okay. So what about cosine? So cosine's on the x-axis. If it's what happens if it's odd? Let's do the odds for now. If it's odd, we still get the origin and the positive x-axis. If it's 5, we still get the origin and the positive x-axis. If it's 7, we still get the origin and the positive x-axis. So for cosine, we always get a loop on the x-axis, on the positive x-axis. For sine, remember, it alternated above and below. What about if it's even? Here, well, we now hit all 4 axes. Remember, with sine, we don't hit any of them, just the origin. So with 2, we hit all 4 axes. With 4, again, we hit all 4 axes. With 6, we hit all 4 axes. There's a bunch more stuff going on, but we hit all 4 axes. And remember, with cosine, we didn't hit anything except for the origin. And again, it's crossing the axes on the radius of our circle out here. So it's crossing it at the value of a. Okay, so plus or minus a, plus or minus 6 on all 4 axes. Okay, so that's sort of the rows. Let's go ahead and move on to our last function. All right, our last function is the limacon. R equals a plus b sine of theta, or r equals a plus b cosine of theta. Okay, so we could have, again, now we have 2 variables, a and b. So we're not going to change anything in front of the n. It's just going to be a and b. And we need to look at, so how do the a and b affect the graph? What's the basic shape of the graph? What happens if it's sine or cosine? And where does it hit the x-axis again? All right, so these select rows open up the limacon. So again, we have a and b. We have sine and cosine. So right now, the graph has r equals 1, sine of no cosine, so no sine. So this is just r equals 1. It's a circle of radius 1. So as this gets bigger, again, this is just going to be a circle. Okay. So let's not do b equals 1. Let's make b equals 1 as well. Okay, so it's kind of a circle, but the bottom of this kind of comes back up and touches the origin. Okay, let's maybe make this a little bit bigger. Let's go to 3 and 3 here. So if we notice this a little bigger, so we get this kind of graph. This is called a cardioid. So it's sort of a circle, but then it's not a perfect circle. It curves back in and touches the origin. Okay, so look at what has to be true for the a and the b value in order for this cardioid to happen. So right now, 3 and 3, they have to be the same. What happens if it was a negative 3? Well, it's the same thing. So 3 minus 3 sine of theta, it's just going to open downwards. Okay, same thing will happen with cosine. Where does it touch? It hits the origin. Where else does it hit the y-axis? It hits the y-axis at 6. So where do we get 6 from 3 and 3? We add them together. Where does it hit the x-axis? You know, it hits the x-axis at 3 and negative 3. So which changes that? Changing b does not change where it hits the x-axis, but changing a does. So it touches the x-axis at 3 and negative 3. Or in this case, we could say it touches the x-axis at 4 and negative 4, because that's the a value. Hits the origin, and then up here it's at 8, which is b plus b, or b plus a, 4 and 4. What happens if a is bigger than b? So there. So if a is bigger than b, we have, it's no longer a circle, it's kind of squashed. We call this a dimple. We can kind of see the dimple a little bit more. There's a dimple here. It's getting close to the cardioid. So it's kind of stretched it from a circle down to a cardioid. But the idea here is it's still touching at 4, negative 4, because that's the a value. It's touching up here at 7, because 4 plus 3 is 7. So where do we get the negative 1 from? Where does it cross here? That would be 3 minus 4. So it touches up here at b plus a, and down here at b minus a. And then if we switch this and make b bigger, now we get this inner loop. So the inner loop, again, it touches it here at 3 and negative 3, because that's the a value. And it touches it at 8, because that's 3 plus 5, and it touches it at 2, because that's 5 minus 3. So b plus a is the top, b minus a is the middle, is the top of the inner loop. And so we call this an inner loop. Okay. If we do with this with cosine, it's the same graph, just pushed over onto the side. Okay, so everything that we've just been talking about still works. Okay. Anyway, keep playing around with that. And go ahead and take a look and work through page 39 in your lab manual.